Okay, in this lecture video, we are going to remove the restriction that the uniform plane wave is propagating in the positive z direction, and now we're going to allow it to propagate any such direction, and we're going to add the math that we need in order to do that and describe the plane wave. All right, so let me go back to these two equations right here, which show for a uniform plane wave, the electric field and magnetic field, when we are saying for sure that it's propagating in the positive z direction. Right, I'm going to rewrite them again so we can recast it. Right, the electric field will have some base phasor value, and we're going to change that phasor by multiplying it by e to the minus j beta z. We're going to assume it's oriented perpendicular to the z direction, so it's in the, let's say it's the x direction, in which case the magnetic field as the phasor will be the electric field. Oh, this is not a vector. Will be the electric field divided by eta times that same e to the minus j beta z. And we got to put this in the y direction so that we can assure that E cross H is the direction of propagation, and that the intensity of E divided by the intensity of H equals eta. All right, but let's recast this now, and let me just get rid of these so I have room. What's worth noticing about this minus j beta z is that z represents the distance in the direction of propagation, right? So as you move along the axis of propagation, z increases, right? So we want to put something here that's going to capture basically how far are you in the axis that points in the direction of propagation. So we're going to recast this in the following form, right? The electric field will be some base phasor value times e to the minus j times beta bar dot r. And h, we're going to write the same way. It's E0 as a phasor divided by eta, and then we're going to multiply that by e to the minus j times beta bar dot r. All right, now the electric field is going to be pointed in some direction, and the magnetic field will be pointed in a different direction. We know that E cross H equals beta bar. It's going to be in the direction of beta bar, or sorry, beta hat. But let's talk about what beta is. All right, beta equals omega divided by the propagation velocity. But beta bar, as a vector, is going to be omega divided by Vp, and it's going to be pointed in the direction of propagation. Right? So that's our definition of beta. It's equal to omega over Vp, that's the length, and it's going to be oriented or pointed in the direction of propagation. Okay, r is the vector of where we're trying to describe the electric field, right? So r is a vector from the origin to the observation point. Now, what's important to note right here is that this term right here, beta dot r, is going to select the component of r that is in the direction of propagation, right? So this is the component of r that is along beta, right? So in other words, if I have a wave that's moving this way, this represents our beta direction. And right, if I take this as the origin, and let's say this is the vector r, then I would expect everything to be the same here as it is at the origin, which means that r basically has no impact, right? R dot beta or beta dot R is going to pick that component out and it's going to set this as effectively being no different from R being at the origin. If I set a value of R that's over here, if I say this is R, now it's going to pick out this component right there, and the length of this segment is going to be R dot beta bar, right? So in that sense, this beta dot R is equivalent to the beta Z that we had before, but it's now generalized because beta can be in any direction that we want, and R can be in any direction that we want, and it's still going to describe how the phase changes with any location, right? Now this quantity beta is very important because it simultaneously tells us what is the wave number, what is the radians per meter changes as we sort of walk along in the direction of propagation, but it also tells us the direction. As a note, in some fields, you'll notice beta being replaced with K. That's effectively the same thing, and we'll see in the next lecture how we can generalize beta, but for now, we're just going to take beta as being correct. All right, with that, let me just reiterate this important feature, that beta hat is a unit vector in the direction of propagation. And if we take the direction of the electric field and the direction of the magnetic field and take the cross product, we get a vector that's in the direction of propagation. So both electric field and magnetic field are perpendicular to each other, and they're perpendicular to the direction of propagation by virtue of E cross H equals beta bar. All right. So with that, we have now basically described the key elements that make a uniform plane wave. But in the next few lectures, we are going to remove a couple of the complication that a couple of the simplification that we've made, starting with the idea that the medium is lossless, right? Real media will have some electrical conductivity. And we'd like to be able to describe how radio waves will propagate through those. This is important. For example, a GPS signal in a satellite. If it's propagating to you underground, it's going to pass through, for example, concrete in the floor before it reaches the basement. As it turns out, that's going to attenuate and destroy the signal as it crosses through. In the next lecture, we're going to talk about exactly how we quantify that. In order to do that, we're going to have to slightly modify this relationship that we have on the board.